Go. All right, we're live. It's March the 5th. Okay, let's take a look at today's challenge. We have a notification. Take a look. Oh, it's just about, I think it's about yesterday. Got 10 coins from yesterday. That's good. All right, let's take a look at today's challenge. Average of levels in binary tree. Binary tree. Oh, only have one example. Given a non-empty binary tree, return the average height. No. Not average height. Average value of the nodes on each level in the form of an array. So 3, 14.5, 11. Oh, okay. The range. All right, so this is going to be a BFS. All right, let's do this. It's going to be a BFS. We can write a straightforward BFS, I think. BFS, we just need to record all the values at each level. And we're going to do the BFS. Yeah, let's just do the BFS. The most traditional way of doing BFS. Alright, again, this is another day that we're not going to run test cases on ourselves. Alright, so for BFS, let's do it in the right way, which is from collections, import deck, and we're going to call it a queue. So a queue is going to be a deck, and we're going to put the root in it and the level in it as well. We also need a result. It's going to be a list. All right, so we're going to say while queue node level equals queue dot pop left, and I'm going to say current level. Current level is 0. That's our level. All right, and then we say res 0, right? And then we say, oh, we also need to count how many are there. That'd be a better way of doing this? Yes, it's a better way of doing this is to have a res and have a temp. Let's call it temp. Temp will record all the values in the same level. So I'm going to say if level equals current level, I'm going to say temp.append node.val. Else, if it's not the same, res.append sum temp. And the sum temp and divided by length of the temp. All right, and then we're gonna clean temp. Once we are done, and then we say if node.left, then queue.append node.left and level +1. If node.right, queue.append node.right level +1. We probably also have to take care of the current level. So if it's not the same, after we do all this, then current level has to equal level. Right? We actually do this every single time, but no, let's not do that every single time. So let's kind of run it. So the first one will be the root. Level is the same, temp append. We'll go left and right in. Next one out. Next one out, level is not the same. We'll go here. So we're going to append whatever is in the temp. Temp clean. New level. Current level become new level. And we're going to do the next one. Next level one. Coming back again, it's going to be the right child. So it's still be the same, so we're going to append another thing. I think it's correct. So we're going to return. Return res. Yeah. Return res. All right, take a look and run the test case. We only have one test case, but we can create more test cases. That's fine. Not a big issue. Ooh, cannot unpack. Did you not append the right thing? Oh no, you did not append the right thing. I forgot the... Oh wait, this is also not right. It has to be this. And we're gonna append, always appending a... Yeah, it's gonna append a tuple. It's not right. We get 3 out. We get 20. How is it 20? It didn't get 9. It didn't get the last one. Alright, that's weird. Can we not run this right? We pop left, right, and then we append the left and right node. Temp.append node.value. Yeah. And then sum this divided by length. Alright, let's take a look. Level is equal to current level. As the level is not equal to current level, and I set current level to this. What is the issue here? I got 3. 3 is in. 3 comes out. And then, are we saying that 9 didn't get in to the queue? How come 9 did not get into the queue? It's probably the transition of the level we have some issues, right? So 3 level is the same. No, temp append 3. Okay, node left is good, so we push 9 into it. Level become 1. Node right is 20. We'll push 20 to it. Level will be a 1. Yes. On to the next one. Pop power is going to be 9. And this is going to be 1. 1 is not equal to current value because the current level is 0. So we do this. Rest of append. So that's the sum will be 3 divided by 1. So that's the 3 coming out. That's correct. And then we clear out the temp. Oh, we clear out the temp. We did not add the node value. That's why. So we have to add node.val, and then we set current value equals level. Current level, we change current level. And then we push, there's nothing to push because 9 has no children. Coming back up, now 20 comes out. 20 on 1 equal, so 20 get pushed in. 20 has left, so we got 15 and 7 pushed in. Come back again. Level is not the current level, so we do okay. So the rest should be appending the average of 9 and 20. Level reset, and temp is 15. We put 15 inside. No children. Coming back, the last one 7 comes out. Equal come out. So we have to also do this one more time. I have to do this one more time at the end, because if we don't do it, the final one will not be encountered. So that shall do it. Okay, so let's run some test cases on the extreme case. For example, empty. Yeah, always like to have empty. Okay, so empty does not pass. Why? Well, root, I call root.val. So we probably have to, what should we return? if it's an empty. Huh, very interesting. If not root, when return what, an empty list? Is that how it's supposed to be? Oh yeah, an empty list. All right, edge cases. Now we have it. One node shall work. Let's try some. I think no 1, no 2, no 3. Yeah, something like this. Let's see what's gonna happen. Some edge case. Yeah, I think this was right. 3 test cases. Yep, we got it. This is an easy question. Easy tree question. But my initial attempt was not too successful. So I forgot about this part. I mean, now looking at it, we're going to append no matter what, right? So we don't have to do this. All we need to do is say, if it's different, then we're going to do this no matter what. If it's different, then we handle this, and we reset the temp. We do this, and we add this, right? So we don't have to consider 2 different situations. And eventually, kind of want to put this one also inside, but that requires the queue. No, I don't think that's possible. Queue have a temp. We probably can set it to -1, and we only need a rest. We don't need to set up 4 because this will not be the same. And we cannot do this. The temp has to have something. The temp has to have something. Okay, the temp has to have something. So we have to be 0. The temp has to be, otherwise we cannot append the result to res. The temp has to have something. And that's good. So this is to check whether we have finished a level. So the temp has to contain something. And we reset it, and we reset the level. That's good. We always add a new value in, no matter what. Run the code just to make sure, and it should have the same performance, but we just kind of make it look a bit nicer. Fewer lines. Fewer lines didn't mean it's always going to be more readable, but here we know that the temp has to always append something. All right. I mean, it is possible. Yeah, it is also possible to do this. Oh well, let's write a DFS as well. So it's a BFS, straightforward solution. Directly collect node values at each level and compute its average when a level has exhausted. ON, because every node has to be visited. And we run at 48 milliseconds. The first attempt is always, I think, always has higher ranking. I think this might be intentional. I don't know. All right, so we have a BFS, right? So let's try a DFS. I kind of have an idea for DFS. So the DFS is the same thing. You just DFS everyone. So we can def DFS node, tree node, and we'll probably need to have level. We need to have a level in it as well. Now we're not returning anything. And we say if not node, if node, so we don't have to consider not node. If node, we're gonna append. So what we have is let's call it table, is going to be, what is the table going to be? The table is going to be for each level, we're going to, how do we do this? We don't know how many levels there are. So each level we have to push it in, but we can check the kernel length. So it's just going to be like this, right? So if node, and we're going to say if level. So a level going to start with 0, right? When we say level, going to start with 0. So when we say level, if it's equal to land table, that means this level has not been visited before. So I'm going to say table.append, just empty list. And then I'm going to say table level dot append node.val. And then we're going to say dfs node.left, dfs node.right. So we visit all of these, and then we call dfs on the root, and it's going to be 0. If we call it table shall be populated, we're going to return. What do we return? We're going to return a list. I'm going to say for say vowels in table, right? Let's just call it rows in table, right? Rows in table, and for each row we're going to calculate its average. So it's going to be sum rows divided by len rows. Not going to be rows, it's actually row, just rows, not rows. Each row. So we're going to do just row. And we're going to run this as well, see how this one works. Run. Let's take a look. Missing one required position. Oh, I forgot to do this. +1, level +1. Run again. That one's correct. Let's run the given test case. It's not really like given test case. We just put some other values into it. Okay. Run it again. We got good. And finally, we're gonna run with empty list, empty tree, and we can handle empty situation directly, which is good. So we're gonna submit this, and it's going to pass. That is correct. So it's the, oh, it's slower. So this is the DFS. Also pretty straightforward solution. At when visiting each node, we push the node value to an external table that records the values of each row, and eventually we can compute the average based on the external table. So this is also ON, but we also have to incur this, but it's still ON, right? Everyone only visit twice actually. Everything visited twice, and we hit this at 56 milliseconds, which gives us a 38% ranking. Is it possible without relying on external, so we can just have a result? Let me see. Is it possible? I mean, we can do, so instead of table, right, we can put rest here, and we can just accumulate the values, and we just need another one. Yeah, we just need two lists. One is to accumulate the values, and the other is to compute the total number of occurrences of nodes at each level. Is it possible we can combine these two together? Well, I do not know if it's possible to combine them together, because if we want to combine them together, we need to figure out a way to count and to accumulate the values in a single cell, which might be possible if we do some whatever bit manipulation. Maybe, I don't know. I'm just thinking. We'll have a sum. Is it possible we also know how many times we have produced the sum? You know what? I don't think it's possible. But what I want to do is to have 2, so we can reduce. So we don't need this. Right? This is just extra work. And then we have here is also whenever we call sum, we have to redo a lot of work. If we have, like, say, yeah, we can actually change this one as well. Instead of a temp, right, it is going to be something different. All right, we can change that later, but let's do it here. It is easier to think about. So we say if level is the same as rest, and then rest and count should grow at the same time. So if it's the same, then we say rest.append 0 and count dot append 0. So we have 2. All do this, and then we say rest level is going to be plus equal to but then it is log n, because we just do the levels. We won't have to do the compute each level. We'll just go from level to level. So it's going to be note.val, and we're going to say count level plus equal 1, right? And then we visit these. And at the end, what we're going to do is there's going to be no sum call. It's just going to be for, I don't even want to call it res. It's going to be cumulative. Or let's call it level sum. Yeah, let's call it level sum and count. Right, level sum and level count. Let's be more explicit what these are. Level count. So we're gonna just do for sc in. I'm gonna zip them level sum and level count. Right, I'm gonna zip them, and all we need to do is just do s divided by c. So this thing shall be faster, because we only engaged in on instead of O2n, right? If you know what I mean. Actually, these description is now correct, I think. Oh, you don't have to run this. We know this one passed. Like yeah, anything will work. Let's take a look. You forgot? Oh, I didn't do it. Oh my goodness. I didn't copy the correct one back. So we always have this issue. And I think we work. I'll just go right for it. Pending judging. Is it faster? Yeah, it is faster than before. We know it's good because this reduces. Use extra space. Actually, not even extra space. It's the same amount of space, right? It's the same amount of space, and we can reduce the sum call. So it become on plus o log n. There's also the same level of same number of lines. Pretty straightforward. When visiting each node, we add the node value to a list that tracks the sum of values on each level. We also increment a counter for total number of nodes on each level. And eventually, we compute, right? Eventually, we can compute the average based on the level sum and level count. Level sum and level count arrays. And this one we received slightly better performance with 52, and we have a 55% ranking. And we can use the same idea here as well. So instead of have rest and temp, we're going to do the same thing here. So it's going to be level sum and the level count, right? So if it's not the same, okay, I think this is slightly different because we're visiting each row at the same time, right? So that means we need to have level sum, level count. Yeah, that's fine, level sum and level count. And then we just say, we don't even need to have a current level. I think we can use the same logic. I'll just say if level is equal to len level sum, that means it's a new, we're entering a new level. Then what we do is we're gonna say level sum dot append a level sum dot append 0 and level count also append 0. After they append, we are going to add the value. We're going to say level sum level plus equal to node.val and the level count, same thing, level plus equal to node plus equal to 1, right? And then we visit, and at the end, I think that's exactly the same. We're doing exactly the same logic, just one is DFS and the other is BFS. I think that's the only difference. That's the only difference. Okay, probably can even remove this. While Q node, yeah, and we just if node, right? If node, then we do all these, and then we don't need this. Pretty ugly at the beginning, and we don't need to do this as well. But then we are going to increase the runtime a little bit. That's checking here. I mean, we can reduce. Yeah, let me just remove this. Now this is exactly the same as the DFS solution. Okay, let's take a look. This is the exact same as the DFS. We just written it as BFS. Yeah. And I think it can handle empty as well. And it should naturally be faster than DFS because it's imperative. There's no recursion in this. No, it's not. No, it's not. So, are you saying that adding the check is important because we reduce the number of time we need to run the loop? I don't really think so. I think it's the same. You're just micro optimization, which is not recommended. Anyway, so are we going to record? Let's just be honest. We run at, I forgot what did we run at? This one we run at 56. That's fine. Doesn't matter. Let's have 32. Let's say BFS. Same logic as DFS. the exact same logic as DFS, except we're running it in a BFS. Not sure if it's like faster or slower. You know what? I probably should just take this as another solution, and we're gonna get our original back. Yeah, because there are difference in these solutions, right? So this is just a BFS, the BFS version of the DFS. So when you say the BFS version of the DFS, and previously we did have a true, I shouldn't say true, another BFS solution. Let's go to solutions. I'm not going to read it yet. I want to recollect. Oh my, I ran so many times today. All right, so this is the original one. Yeah, this is the OG solution. No, I'm not going to copy everything because I need only this. This is the OG of everything. Everything starts here. Yep. So that's solution 2. What are you doing? We don't want to change solution 2. We're going to change solution 1. There we go. So there's our 3 solutions. They're all the same. Nothing too. It's going to be an easy question. Oh, we have 3 easy in a row. DFS. Do we have count and rest? Yep, count and rest. And what is this? Average of levels. This is average. I call average. Oh, I call average set. It's fine. I had 1. Yep. BFS. It's the same idea. I think this is the. Oh, we can have a count. Ah, so each level can have a count. Ah, now I see. Oh, we don't need to use. Ah, yeah, because for each level we are. Oh, yes, I know the trick. Okay, so for this one, we don't have to do this. Yeah, why bother having a list? Because every time we switch to a new level, we can always reset, which is absolutely correct. We can always reset. So it's when it is the same, then we are going to. So we don't need this, right? So it's just when this is the same, we're going to reset. We're going to say S and C, sum and count equals 0 and 0. And we just say S gonna do no.val and C gonna count and blah 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 blah. And once but we don't have a level, so we need a level, and we need the current level 0, and we say equals current level. When it's equal current level, then we do. But when do we update? So we still need a res, right? We need a result. We still need result. So it's going to be if it's not the same. So yeah, it has to be it's not the same, because when it's the same, we keep accumulating. It's only when it's not the same, we reset. And before we reset, we need to append on the res. It's going to be S divided by C. And then we reset this. And we reset this, and we do this, and we do this, and we return res. Okay, let's try that one more time. Here, not really. This is right. Okay, let's take a look. We have runtime error. Variable S is referenced before, which is correct because I never set S before. So we have to set S here and run again. List object has no attribute. It's double P, not single P. That's a spelling error. No, it's not correct. We just append the numbers inside. That's weird. Oh, because you never. Oh my God, why just leave it hanging like this? Unbelievable. And I just realized we have to also do it at the end as well, just like we always do. So after it's done, we have to append. I kind of don't want to append. That's just plus s divided by c. Yeah, like this. That should be right. Yeah, that is correct. And we can also test an empty array. Empty tree shall work as well. Empty tree does not work. Why is empty tree not working? It says division by 0. Oh, that is correct. Cannot divide by 0. Huh. How do we resolve this? I don't want to just like, does the official solution has a check on the? It does not have check. How does it solve the empty situation? Oh, it has two. It has two while loops. This is the actual logic, and it has another one. Huh. Oh, I see. I see how this logic works. So every time, is that the official way of doing BFS? Like every time we'll create a new. I see the point of doing this. Every time for every level, I create a new queue. Because of this, I don't have to. But then what? Then what's happening? We have a new queue, and then we take it from the outside. We do all this magic, and then we append it into temp. Okay. So we will consume everything from the current queue, and we assign temp to the new. Oh, okay, I see. I see how this one works. Maybe I should do it now as well. So we have two queues. One queue is, basically still one queue, but for every level, right? For every level, we have a queue, and when we traverse this level, we put the value into a new queue, which is its child, its lower level, and we traverse through the current parent level, and when we're done, exhaust that level, we have created the next level, and then we just swap it. I think that's actually maybe this is how I am going to redo all the BFS I've ever done. Because this way we can avoid this ugly thing called level, right? We have this level because we need to track which level we are at. But if we have two queues, we don't have to use a level. I think this is a better one. I think this is a better one. I like this. I'm going to change how I write BFS from now. So I should say a better BFS without the need of using level. I've always been wondering how this is achieved. Now I know, right? So we probably need to use rest as well. And we don't need to use this. So we're going to say queue, right? While queue, what do? We need to create a temp. So we need to have a temp, which is just next level, right? The children level is going to be a new deck, but this one is going to be an empty queue. And then we're going to have S and C set to be 0 right here, right? It's going to be 0. And then we're going to while queue again. So we're going to traverse this queue, and we're going to say node equals queue dot pop left. Let's try. That's right. And we are going to say we're just going to be S going to be, because this all belonging to one level. So directly we don't need to check anything. So C is going to be this, right? We do this until we finish, and also the children. Yes, the children. So the children will be append to the next level. So we say next level gonna append, next level gonna append. Just append this, right? Just append the node itself. No level involved, right? And while queue, we can also use some magic. And node, yes, like this, queue dot pop left, right? Line a node. So we don't need to do this. We'll save another line, and we can handle the node when it's empty. And then we do this, next level append, next level append. Once the queue is exhausted, then we're gonna say rest.append. We can append S divided by C, right? And we're gonna assign Q equals temp, because temp is not temp, next level. Q will equal the next level, because that's the children level. So 2 while loops to handle this without the need for a parameter called level to keep track of levels. Yeah, that's the spirit, right? That is the spirit of BFS, I think. All right, let's take a look at this. First of all, we run the empty case. Cannot use assignment. Do we have to do something like this? It's just still some kinks to work out with the operator. We still have the issue of division by 0. How do we deal with this? Sum times 1 divided by count. Does that even work? How does this one handle the empty? It's exactly the same, right? So we have this not empty, and then we remove it, we plus it. Oh, we did not push. Okay, so there's going to be nothing pushed in. But if we have an empty root, right? If it's empty root and is an empty root, and they're not even checking on the empty root. So I think this one will fail, actually. I think this one will fail. Hold on. This is Java, right? Yeah. Let's run this on Java, on whatever solution the official provides. We're gonna run the same one. I think this one shall fail. Yeah, this one failed. Yeah, this is not the correct solution. They provided one. The official solution is not correct. But let's go back to our problem. Our problem is the same, right? So, I think we'll have to do a check here. Yeah, we have to do a check. So we have to do a check. If C is 0, if C is not 0, then we append. Otherwise, I don't see a solution out. Yep, there we go. And let's test something. No. That shall work. That does not work. Why? Why is that not working? Let's see. To the next level, the last level. Q. Rest dot append. Hold on. Why is this one not working? Let's see. A tree visualizer. Okay. What do we get? We get 2, 3.5, and we output 31. Expected 22. What is 31? 31 is 31.5. Is 56 plus what? Plus 7? 63? Yeah. So 4 is not included. How come 4 is not included? I append the right and I append the left. That is interesting. That is very interesting to say the least. Okay. Node equals something probably wrong with this. I'm trying to be smart. While Q, right? And we pop left. But we have the previous, like the 3, 4 is correct. Ha, very interesting. Do we have a problem? Let's say a very simple case, just like 2, 3, 4. Will this one work? Well, it's always the last one that's the problem. 2, 3, 4 works. And let's put null. Put a 5. See what it looks like. I guess this one shall work as well. No, this one does not work. 5 is not output. 5 is not output. So 2, right? And then we have a Q and Q, and we pop the node out. 2, S is 2, C is 1. Append the next level, left and right, 3 and 4 coming in, and going back. And Q now is empty, so we jump out. C is now 0. Rest dot append. So the first level, first value is 2. Okay, so 2 succeeds. And then the Q equals next level, coming back up. The next level reset, SC reset. So our Q, so 3 pushes out because I say pop left. And S is going to be 3, C is going to be 1. And go to the next one. So left. Oh, I think I know why. Because I append the left, I have none. So this one was none. And it only goes if Q and V. So if these two both satisfies. Okay, I see the problem. So that means for this idea to work, yeah, because we cannot end it. All right, so it has to be, yeah, I cannot be using Walrus here, because Walrus will end this Q, will end this while loop immediately, which is not correct. So we have to do it outside. So node is this, but then when you check if node, and then do everything. Oh my goodness, this is so ugly. Let's try if not node, continue. All right. I mean, all this is to say that I want to handle. Nah, this is too ugly. I don't like it. I don't like it. No, I do not like it at all. But then we have to add 2 more lines here, right? We're going to check the left and right before we push it in. Hmm. Huh. This one shall work. Yeah, I think let's just leave at this. Yeah, let's just leave at this. The best effort. Oh, look at this. That's good, very good performance. Yeah, let's just leave it at this. It is a better one. Yeah, I think we end up just to add a few more things, right? We added this as needed, and we have to do this to prevent the initial problem. All right, this one. I hope that in the future, DF whenever I try to write BFS, I will remember this way of writing. I think this is the official, correct way. And this captures the spirit of DFS. All right, that's it. I don't think it's necessary to go through the discussion. Nothing more. Oh my God, he has a one-liner again. What the heck? Integration to copy and paste solution. Oh, level. Ha! Cheeky. Binary tree level order traversal. Copy and paste from old problems. Anyway, we know. All right, that's it. That's it for today. I'll see you guys tomorrow. Adios.